Welcome to my YouTube channel where I discuss things related to data science. This video covers how to perform principal component analysis with Python, concepts, implementation, and visualization. These are the celebrated opening lines of 20,000 Leagues Under the Seas by Jules Verne. The passage tells us that the year 1866 was marked by a strange and unexplained phenomenon that captured public attention and greatly disturbed seafarers. France is not only known for its rich literary heritage through authors such as Jules Verne, but also for products that have become parts of its cultural identity. One of the most famous of these is wine. In this presentation, we will use a wine dataset as an example to demonstrate how principal component analysis can help to understand complex data. Here we see a dataset describing different wine samples. Each sample is characterized by several measured features. While such tables contain a wealth of information, it can be difficult to identify patterns simply by examining rows and columns. Visualization often makes these patterns easier to understand. By transforming the data into a smaller number of dimensions, PCA allows us to observe relationships among samples that may not be immediately obvious in the original table. This illustrates an important aspect of data science. Data scientists not only understand the language of data, but they can also analyze it and draw actionable insights from it. Equally important is their ability to communicate those insights effectively. Just as authors such as Jules Verne use words to tell stories, data scientists use data visualizations and analytical techniques to reveal the stories hidden within data. A table of numbers may appear unremarkable at first glance, but the right analysis can uncover meaningful patterns and transform data into knowledge. Machine learning. It is the application and science of algorithms to have better understanding of the information present in the data to gain relevant knowledge. This will enable better data-driven decisions in that particular domain. These applications can be found across many different fields from healthcare and finance to weather prediction and food quality assurance. There are various ways to classify machine learning. One of it is based on learning approaches. Supervised learning is the most popular type of machine learning. This involves learning from labeled data, meaning the desired output signal. The words target and label are generally treated as synonyms in supervised learning, but target is more common in regression tasks and label is more common in classification tasks. If the data is categorical, discrete, showing different classes of samples, it is a classification problem. When the concerned data is continuous value, like house prices, the problem is a regression problem. The second approach is known as reinforcement learning. This approach is centered around the concept of learning by interaction. The goal is to develop a system or agent that improves by interacting with the environment. It selects and performs actions and get rewards in return or penalties in the form of negative rewards. It has to choose the best strategy called a policy to obtain the most reward. The program AlphaGo that beat the highest ranked Go player in the world in 27 was trained using reinforcement learning. The development of such a program was considered a great achievement as the number of moves in the game Go are much greater than that of chess. Another approach is unsupervised learning. This approach is used to explore the structure of the data to obtain meaningful information without guidance or being taught of the outcome variable. Also, there is no strategy of reward or punishment. The training sample is unlabeled and it learns without being taught or guided. In many applications, it is often later coupled with supervised learning to classify the samples. The two approaches to discover hidden structures in unsupervised learning involves dimension reduction to compress data, which will be shown later. Another approach is to cluster to find subgroups as shown below. In a nutshell, supervised learning involves initial training or being guided, whereas unsupervised learning receives no feedback, whereas reinforcement learning, the algorithm tries to develop a strategy to achieve some goal. Dimensionality reduction for data compression. Dimension reduction compresses the data into a smaller dimensional subspace while maintaining most of the relevant information. It is a feature extraction where the technique derives information to construct new feature subspace from the original feature set. A key benefit of dimensional reduction is that many algorithms work better when the number of features is lower. If the dimensionality is large, the data becomes sparse in space that it occupies. This can mean that there is not enough data objects to allow the creation of a model that assigns a class to all possible objects for the task of classifying them. One of the primary advantages of dimensionality reduction is that it enables the visualization of high-dimensional data, since humans are generally unable to perceive relationships beyond 3 dimensions. Principal Component Analysis, or PCA. It is the most popular dimensionality reduction algorithm. It is a statistical tool that uses orthogonal transformation technology. It is a linear algebra technique that identifies the axis or principal component that amounts for the largest variance in the data set. It then finds the next axis, PC2, that is orthogonal to the first one, that is responsible for the largest amount of the remaining variance. Often, the number of PCs used are less than that of the original features. The most popular language for machine learning is Python, and this programming language is used for the analysis. The user-friendliness, readability, and simple syntax of Python, as well as the numerous tools and libraries, make it arguably the most accessible programming language. Python has also gained popularity among data scientists and machine learning engineers over R, the previous dominator in the field. This analysis is carried out using Jupyter Notebook in PyCharm Professional. Briefly, the steps in PCA involve importing the relevant library, importing the particular dataset, splitting the dataset into training set and test set, carrying out feature scaling on the data. Here, the mean and standard deviation are calculated from the training data. These are then used to scale the training as well as the test set. Then, applying the PCA technique. This involves singular value decomposition of the data matrix and then visualizing the training set as well as the test set. The codes for running principal component analysis in PyCharm Professional is shown. The analysis can also be done with Google Colab. The first steps involves importing the libraries NumPy, Matplotlib as well as pandas. The second steps involves importing the wine dataset from the UCI machine learning database as well as defining the columns. X, the chemical parameters of the wine dataset is selected using the function locate indexes. All the rows and the data in column 1 to 13 is selected. Take note that the indexes in Python start from 0. Next, the data y pertaining to the class of wine which is present in column 0 is defined. This parameter is only used for visualization purposes. The function yHead shows the first 5 rows of the data. The function train test split will be used to split the data into training and test set. The ratio between test size and training size is 0.2 for test and 0.8 for the training. At this stage, the package scikit-learn will need to be installed in PyCharm. The standard scalar class in pre-processing module of scikit-learn is needed to scale the data. The function fit in standard scalar module is used to calculate the mean and standard deviation for the training set data, and then it is used to transform or scale both the training as well as the test set. The PCA class in decomposition module of scikit-learn is used to carry out principal component analysis. The number of PCs to be calculated is 2. As we want to visualize the separation of the 3 classes, we choose 2, and if the results are not good, it can be increased. The fit transform obtains the 2 PCs by SVD, and X-train reduced are the scores calculated for the scaled X-train data in these two X's. The explained variance ratio shows how much of the total variance is explained by each of the principal components. The X-train reduced shows the principal component scores for the X-trained sample in PC1 and PC2. X-test reduce are the PC1 and PC2 scores for the scaled X-test data when the test data were projected onto the PCs calculated earlier by using the transform function. Each of the 13 parameters have a loading for principal components. When each of these loadings are multiplied by the scale parameters for each sample, the total value gives the score for the principal component concerned. The codes for obtaining the scatter plot for the trained sample is shown. For obtaining the plot for the test sample, the word train has to be replaced by the word test. Next, we will look at the implementation of the codes in PyCharm Professional. The scatter plot for the PC1 and PC2 for the training data and test data is shown. Three samples of class 2 occur in the region of class 1 and another shown by the green arrow is present among class 3 samples. For the test samples, the separation between classes is good. Take note that the color coding of the classes 1, 2 and 3 are for visualization purposes and this information of the classes were not used in the principal component analysis. PCA, like any other machine learning technique, has its advantages and limitations as shown below. In this part, we look at a reduction technique. Often, the results of this can be compared with a clustering technique. Alternately, the reduced data could be used in a supervised technique for classification. Like any analytical tool, PCA is not a complete solution. It is one of the many methods available to help us understand data. And in future videos, I hope to explore some of these concepts further. Understanding grows through exposure and practice. Spoken languages and programming languages both have syntax, rules, and patterns. Python was used in this presentation, but R could have been used as well. As with spoken languages, experience with one programming language often makes learning another easier. The goal is not merely to learn a language, whether programming or spoken, but to use it to communicate ideas, solve problems, and discover insights. Thank you.